In this series of videos I'm attempting to repair this Televideo TS800A computer. It's actually a combined terminal and computer in one case, but the two parts are completely independent, just communicate through an internal serial link. And I found several faults with this already. There was a failed capacitor in the supply, so I replaced that, tidied up the supply, and that was then working fine. But the Z80, so it's a Z80 computer and the 950 dumb terminal in effect, and the Z80 computer wasn't booting up, it was staying in reset. That reset's supplied or controlled by the 6502 dumb terminal side. So I popped the 6502 processor out, and that allowed the Z80 to come out of reset, and it started going through its self-tests. I had already replaced the DRAM, and so I know all the DRAM was fine. I had a stock bit which I found with the Fluke 9010A, and I then resorted to the Logic Analyser to find out what was going on, because the first self-test step, which is the RAM, was failing. Found the issue there. That was a failed 7474, and that was preventing the CAS signal getting through to the DRAM. I then off camera found a kind of failing multiplexer, which I've also replaced. That's just two of the Glue Logic chips replaced. I have put a new processor in this. I'll more than likely put the old one back in when I'm finished. The only reason I put a new one in is the pins on the original were fairly badly corroded, and I couldn't easily attach the Logic Analyser probe, and I don't want to start scraping too much material off the pins. They're fairly thin already, but I'll think about that later. The self-test then got through to the second step, and it failed that. That was a DMA controller, so I've replaced that. Then got through to the third step, and then that's as far as we got in the previous video. That test step just kind of hung. The LED came on, which indicates the test is underway. If the test fails, it's supposed to start flashing, but the LED just came on, stayed on, and that's as far as it would go. So the next thing I did, following on from the previous video, is I put the Logic Analyser back onto the Z80, booted it up. Wasn't triggering on any particular address. I just assumed it was going to be stuck somewhere in a small loop, and sure enough I found that it was stuck in a small loop where it was waiting for the transmit buffer clear bit to be set in the status register of one of the SIOs, and the channel it was waiting for was the internal serial link channel that talks to the 6502. So it looks like one of the test steps is to send some data through to the 6502 and then wait for a suitable reply. And going further back through the code, reversing back through the code, I found that the Z80 was indeed loading some data into the transmit register, and then just sitting waiting for the that register, the transmit register, to become available again to indicate that the byte had been sent. But there's no timeout, it was just sitting there indefinitely. Now of course it wasn't going to get a reply from the 6502 because the 6502 wasn't plugged in. So it's kind of a catch-22. If I put the 6502 back in, the Z80 wouldn't come out of reset, so it wouldn't run the self-test. But if I took the 6502 out, the self-test hung at that point because there was no 6502 to respond. So I then had to switch my attention to the 6502 side. I actually disassembled the code for the 6502, had a quick look through it, so I kind of get my bearings, so to speak. And before I attached the Logic Analyser, I decided to have a quick poke around on this side to see if anything was obviously amiss. So I popped out the two interface chips. That's the 6551s, tested those, they tested fine. The display control chip may work, may not, I haven't tested that yet. I popped out the three SRAMs, tested those, they all test fine, they're 6116s, and there's three of those there for the terminal. And tested the 6502 in the IC tester, that tested fine. And then we have basically what amounts to a general interrupt controller and interface controller at the bottom here, and that tested fine as well. However, when I put a scope onto the 6502, it was completely dead. It wasn't doing anything at all. So I checked the reset, and the reset was doing what it should do. It was going high. the device was getting a clock, a nice clean clock, plenty of amplitude. I tested all the other control lines to make sure that it wasn't being just prevented from running, and they all looked fine, but it just wasn't doing anything at all. Now, as I said, I had tested it in the IC tester, but I took it back out and put it into another machine, and it ran fine in that machine. So I put it back in, but it was still completely dead, and I couldn't find any reason. Even if there are other faulty devices, it should still do something, and even from power up it did nothing whatsoever. So as you can see, I've replaced it. This is the original. I put a different type in just to see if it made any difference. I also checked the pins and the socket, and that was all fine. I buzzed it through from top to bottom and all the pins were properly connected. It just wasn't running. Put a new one in, powered it up, and where we're getting now, if I switch this on, notice that the LED is now coming on, so the Z80 has now come out of reset. It's gone through the self-test, and it's got as far as step 3, where it was hanging before and the LED was just staying on. But now it's flashing, indicating that it's got a bit further, so it's got probably got a response of some sort, but it doesn't like it, or it's moved on maybe to testing the second SIO. I don't know if either of these actually work, but it is now doing something different. So the processor can go into the naughty corner with the other devices, and the next step of course is to reattach the Logic Analyser to the Z80 and see where it's getting in code and figure out what it's actually looking for and why this test is now failing. I've reattached the Logic Analyser, so we'll now use it to try and figure out where the machine is currently getting to and why the self-test is failing at the current point. Incidentally, I do have two separate technical documents for this machine, and they both list the order of the tests and the meaning of the LEDs, but they are different. It says different things, so I'm not absolutely certain of the order of the test. I'm fairly certain the first test, the first LED, is a RAM test. I'm fairly certain that the second one is DMA, but I'm not sure about the third one, whether it's testing the SIO or the CTC, the timer chip, and that's what hopefully we'll now figure out. Now, when the third LED was coming on and stalling, it was definitely talking to one of the SIOs and waiting for the transmit register in the internal serial port to be ready, and it was never ready because the 6502 wasn't there. Now that the 6502 is allowing the Z80 to run, the LED is flashing, so I'll power this up. You'll see that it still does the same thing. Goes through the RAM test, DMA test passes, and then it gets to the next test and it's flashing a fail. And that's what we're going to investigate now. Usually I kind of skip through this sort of thing because it is quite tedious and you might find it quite boring, but I thought for once I'll go through this in detail, step by step, the way I would normally do this. Now it's going to seem quite time consuming and convoluted simply because it involves a lot of jumping between the board, the Logic Analyser and the listing, and normally it's actually fairly quick. It's just trying to video it, it's far more cumbersome, which is why I don't normally video it. But I'll go through this particular part of the fault finding process just for anyone that's interested. If it's not the sort of thing you're interested in, you might want to skip the rest of this video. But what we'll do now is we'll start investigating what's going on with this, and the first step, because we don't know where in code it's getting to, so rather than tracing the code through from where we left off, we know where it was getting to when the LED was staying on solid, but it could be a very long way from there in terms of dust cycles, processor instructions between that point and where it now is. So the easiest way to do this is we'll just start the Logic Analyser running without any trigger value. The Logic Analyser will just capture whatever is going on the Z80, and it's most likely stuck in a tight loop. That's normally what happens when these self-tests fail. So what we'll have to do is find out where it's stalling, where it's stuck, look at the code, look at the listing and try and figure out what's going on. As I said in the previous video, I have been through the listing and commented it fairly extensively so far, but it's not hugely detailed. but it should give us a good indication as to whereabouts it's having a problem and what that problem might be. So I'll move the camera up to the Logic Analyser and we'll see what's going on. So I've got my generic configuration for the Z80 loaded. I'm just going to remove any trigger points. And so when we run this now, it will just capture wherever we happen to be in the code while it's running. I suspect the code is stuck in a loop, and the board is still doing what it was. It's just got the LED flashing, so we're stuck somewhere part way through the self-test. So we'll try and figure out what's going on. I'll start the analyzer running. So we have captured something, and what we're interested in here is where we are in the code within the machine. So if you're not familiar with using the Logic Analyser to look at the Z80, what you need to do is just ignore the refresh cycles. So if you look at this yellow trace, wherever the trace is low, that's part of a refresh cycle. So the address at that point we're not interested in at this point, and you should find that each time you get one of these refresh cycles, that address will increment. So it's 20 there, and the next one it's 21, 22. So they're just refresh cycles, you can ignore those. What we're interested in is the instruction, and as I've mentioned previously, if you want to try and figure out where the instruction fetches are, because different instructions in the Z80 instruction set may be followed by parameter fetching as well, what you can do is look at the M1, in this case it's a purple trace, and wherever that is low, that's a opcode fetch. That's the first part of an instruction, a new instruction. So when we look at the listing, address 559 should be the start of a new line. If it's not, we've got something wrong somewhere. So we'll just quickly have a look through and see if we are going sequentially through the code. So we've got 559, 55A, next instruction is at 558, 559, 558, so it's in a very tight loop. We'll go and look at the source code and find out what's going on there. Might just be a delay loop, and we'll have to find some way to jump out of it, but we'll go and see what's going on. This is our starting point to try and figure out why the self-test is failing. So I've got the source code open here. This is just a disassembly that I took from the ROM on the machine, and you can see I've been through this already and fairly well commented it as far as I can at the moment. Usually what I do is just go through and try and figure out where all the functions are, look for returns, that sort of thing, look for the any interrupt handlers. So for example, if we look for the return from interrupt, we've found one here, so this is clearly going to be an interrupt handler, or is most likely to be. And what we can do there is simply start figuring out what each of these individual parts do. Luckily I had a list of most of the port usage on this, so I could figure out what each port was connected to, and I could figure out what it was trying to write to, and then you can figure out what it's actually trying to do. So what we're looking at here was address 558 upwards, so if we scroll down to that, so 558 is down here, and if you recall, the value it was reading there was indeed 0D, and we said that 559 would be the start of a new line, which it is. So it looks like the analyzer is properly set up, we're capturing what we need to, and just looking at this code, it is indeed just a 3 nested loop delay. So this will be quite a long delay. It's obviously waiting for something to happen. You can see I've commented this here. A lot of the code in this ROM is actually configuration tables that are sent through to the 6502. So we don't need to concern ourselves at the moment with what they're doing, just that they exist. But what we need to do with this is, because I doubt this is where it's sticking, I'm pretty sure it'll get out of this, it's just executing code, it's not looking at hardware. So we need to exit this loop, and if you follow it through you can see that once it's exited the main loop, it's going to jump to, just trying to figure out where we are on this. Okay, so what's going on here is once it's finished this delay, it's going to jump back through to the start of this loop. So clearly this is where it's flashing the LED. It's writing to the LED to turn the LEDs on. This is the value it's loading to actually do that. It's sending a similar byte value out of the modem. That's the external RS-232. So if we had an external monitor or terminal hooked onto this, we'll be able to see data coming out each time this occurs. And then further down there's a delay here, and again triple nested loop delay, and then it turns the LED off. So this is just flashing the LED. So it's gone through the self-test, got to the certain point. It's going to call this function, and this function is going to do nothing more other than just keep looping around flashing the LED. So it's not particularly useful to us. It also isn't going to exit, so we need to, there's no point waiting for the analyzer to hit this address, because it never will. What we can do instead is see what called it. So if we come back up here and see what is going to call this function. Now the problem we have is there might be multiple bits of code that will call this. So rather than searching through every single one, what we can do instead is trigger the analyzer on this address and rerun the test and see what called this function by backtracking through the code. Hopefully it'll make more sense when we actually do it. So we're going to trigger the analyzer on address 536 and see what happens. So we'll enter the trigger address we want. That was 536. It is again hex, don't forget. And there's no point just trying to trigger on this straight away. We'll need to turn the machine off, because it's not going to exit this loop until we rerun the test. So I'll turn off the machine, we'll arm the analyzer, turn this back on. And remember, this routine we're looking for is jumped to when the first self-test fail occurs, and that's the point we're looking for here. It might be jumped to if the earlier tests fail, but because they haven't failed, this is the one we're interested in. So we've jumped to 536, that's the correct value, that's what we're seeing in the source code. And what we can do now is actually go back the other way to see what was calling this. So we can ignore these two values, that we're not interested in those, that's just part of the call and stack usage. So we'll go back, and as we can see, the value we were called from, this again is a refresh value, so ignore that, was 79D. So we'll go back to the source code, find 79D, and see what was going on in that part of the code. So we'll look for 79D. And we are here. So as you can see, 79D ends here, and that's a call to that function. If we actually search for this, so as you can see, that is indeed the start of the function we were just looking at. So we found the right place. We'll go back to 79D and see what the machine was trying to do at that point. So if we go back through the code, we can see what's going on here is actually trying to write to the CTC, the Z80 timer chip. So as I said, the test sequences shown in the technical documentation seem to contradict each other. And I think test 3 is not the SIO test. I think for some odd reason it was trying to use the SIO at that point to report the status of the test to the 6502, which is a bit odd because it hasn't yet tested those devices. So it would have been better waiting till it tested those before it tried to use them, but hopefully it will test them later on. But this loop is testing the timer chip. So if we start at the top of this, and again the reason I know this is the CTC is because I've got a list of the out addresses, and 0809 are the channel 0, channel 1 for the CTC. So what it's doing here, it's turning the test LED on for that particular test. Again, it's sending that out through the modem, and then it starts doing a test. So we'll try and figure out what the test is and why it's failing. So it's loading a timer value into 2 channels of the timer. In fact, what it's doing is configuring it for generating an interrupt. So if we follow this, so it's going through, it's configuring the timer to generate what appears to be a fairly short delay, and then it's enabling interrupts, and just after this call it's disabling interrupts. So I suspect this is a delay loop, so we'll find that. So it's the actual function we're looking for, which is here, and it is indeed a delay loop. So what it's doing, this is not really an active part of the test. All it's doing here is sitting in a delay, and presumably it's just waiting for the interrupt to occur. So it's not a particularly long loop, so it's a fairly short test. It's just waiting for the interrupt. We'll go back to where we were. So it configures the CTC, and then it sits in this delay loop for a little while, and presumably at some point an interrupt should be generated. Once the interrupt is generated, it comes down to this. It's going to see what's at this piece of code. Okay, so this is just sending a report, some tabular information through to the 6502. Presumably it's telling the 6502 the test has failed. So we'll go back to the test. And what we'll do here is we'll have a look at the actual interrupt to see what the interrupt is doing. Okay, so all the interrupt is doing is, when it's triggered, it's loading a value of 0 into this address. So it's E0B6. So if you remember that, that's all it's doing. So presumably it's just setting the error code to 0. So we'll go back to the test. So if we go back up this code, so if we look at these lines, at the start of this test, then the value FF is being loaded into that same address, E0B6. So presumably FF means the test has failed. So if we come down to the actual active part of the test, it sets the timer. If there's an interrupt, the interrupt sets the value at this same address to 0. In other words, it clears the error. If the interrupt never occurs, then it gets to this point and checks. So it's checking that address to see if it's 0, and if it isn't, it jumps through to the fault display address. So this is the loop we were looking at earlier where it was flashing the LED. It's a very simple test. Loads a value of FF into this address in RAM, configures the CTC for a short time, a short time loop, and it expects an interrupt to be generated when the CTC times out. It then jumps into a short delay, waiting for the interrupt. Once that delay is complete, it checks to see if the interrupt occurred by examining the error RAM address. So that should be 0 if the interrupt occurred. If the interrupt did not occur, this will still be FF that was loaded up here. Compares the value there for 0, and if it's not 0, it jumps through to the error indication where it just flashes the LED. So that's why we're not getting any further. Clearly the CTC is not generating an interrupt, but just to confirm this, what we'll do is we'll go back to the interrupt handler and we'll set the address of the interrupt handler and see if it's ever actually getting there. So that address is 37E, and we should be getting to that at some point during that part of the self-test. So 37E, we'll go and set that as the trigger on the Logic Analyser. So we'll set our new trigger address of 37E, which should be the interrupt handler. We will of course need to reboot the machine because it's stuck in that LED flash loop at the moment. So turn the machine off, turn it back on. So the RAM self-test LED is on, takes a few seconds, DMA is done, and it's now flashing the LED again. So it's gone through the CTC test and the interrupt was indeed not triggered. So it looks like the CTC chip has failed. It is, by the way, in case you noticed earlier it wasn't fitted, it is now fitted. I did plug that in before we started this, and clearly that device is not working. So this is how I use the Logic Analyser to look at the source code and the machine and figure out what's going on. You can see it's quite a simple process. It's just taking logical steps to follow through, backtrack through the code, figure out what's going on, why it's happening, and what device is causing the problem. Looks very cumbersome and time consuming. It's a lot more difficult to film than it is to do normally. Usually I'll just sit here with the laptop with the source code on it. I can glance at the laptop, look at the Logic Analyser, then it's a relatively easy process. It's just much more difficult trying to film it. So I'll move the camera back down to the board. So I've popped the device out of the board and it does indeed test as faulty. If you're interested, this is an 8430A. It's a quad timer chip, normally fairly reliable, but this one's clearly failed and it's not generating the interrupt it needs to as part of the self-test, and that's why the self-test is failing at that point. So it seems that the self-test order is the RAM, the DMA, and then this device, and presumably the next step will be the SIOs. It is strange that the machine tries to use the SIO before it's tested them, but that's what it appears to be doing. So in the next video we'll get this replaced, see if we get any further through the self-test, and go from there. If you want to see more of this sort of detailed in-depth fault finding, then please leave a comment. As I say, I normally skip through this because it can be fairly tedious to watch, but some people might be interested. If you are, let me know.